Short history of Canada pushing nuclear hopium. Now, there's two words there that might be a little confusing, nuclear and hopium. So what is hopium? Well, obviously it's a blend of hope and opium, which is a kind of a combination of blind faith and addiction, which is based on misinformation. That's why it's not legitimate. Every addict needs a pusher. Somebody is pushing this message on people that nuclear is good and never bad. This is a 1972 comic book, Pushing Nuclear Power and Nuclear Radiation, and it's falsely comparing nuclear poisons with harmless sources of radiation, such as ordinary heat from a stove and visible light from a lamp. The word nuclear refers to atomic nucleus, which is a positively charged, very, very tiny core of every atom, surrounded by orbiting electrons, which are negatively charged. Now, it's the electrical force of attraction between positive and negative that keeps the electrons in their orbits. But the tiny core has a much stronger force called the nuclear force, holding the nucleus together, and it is millions of times stronger than the electrical force. In fact, the nuclear forces, there's two of them, are considered to be the strongest forces in the universe. All chemical energy involves only the outer electrons of atoms. For example, a battlefield explosion, no matter how powerful it is, a forest fire, such as we're experiencing right now, unfortunately, in many parts of Ontario and elsewhere, these are chemical forms of energy. And although they're massively destructive, they're not anywhere near as destructive as the nuclear energy that comes directly from the nucleus. It's millions of times more powerful than any chemical energy. An H-bomb blast, a hydrogen bomb blast, this particular one is equivalent to the explosion of 15 million tons of TNT. That's very hard to comprehend. It's called a 15 megaton bomb. Because we're talking about history here, I've divided it historically into part one. For the first decade of the nuclear age in Canada here, we were concerned with radium primarily. Part two was 25 years when we were providing material for bombs for the US military. 25 years, a quarter of a century. Then part three is nuclear power growth, which is a period of about 16 years in Canadian history, from 1962 to 1978. Of course, those reactors that were built, many of them are still operating today, but the actual growth, the actual building of these things took place over about a 16-year period. Then there was a period of stagnation for almost 40 years, where nothing much was happening in Canada and not much was happening around the world in terms of nuclear expansion. Part five brings us up to the year 2018, when Canada embarked upon what's called the Small Modular Reactor Roadmap, issued by the Canadian government, in hopes that, and this is now 8 years that we have been promised that small modular reactors are going to be the answer to our energy needs going forward. Part six is, I call it Back to the Future. It has to do with present plans, which surprisingly have virtually turned their back on small modular reactors and have now reverted back to talking about the good old-fashioned large nuclear reactors that small nuclear reactors were supposed to replace. So part one is about radioactivity, uranium, and radium from 1896 to 1940. In 1896, a man named Henri Becquerel in Paris, France, discovered accidentally radioactivity. He discovered that certain rocks, and particularly rocks that contain uranium or thorium from the Earth, give off an amazing invisible energy that can expose photographic plates even though they've been shielded from the light, completely shielded. But this penetrating radiation goes right through the shielding and exposes the photographic plate. He also discovered, to his chagrin, that when he carried one of these rocks in his pocket, he got a very nasty burn on his chest, which was very difficult to heal and started to ulcerate. It's called a radiation burn. And it showed that the great power of this invisible energy. Now, you can't see atomic radiation, the rays that are given off by these rocks, but if you put a rock in a device called a cloud chamber, you can see the condensation tracks. These are vapor condensations of the charged particles and photons that are being given off by this lump of uranium ore. And the amazing thing is that this energy has been pouring off this rock for millions and millions and millions of years without ever stopping. And it will continue to do so for many more millions of years. So scientists were amazed that a rock, just a rock, can give off such energy. They had no idea where the energy was coming from, but they called it radioactivity. And they started exploring it, of course. And one of the people who explored it was a brilliant chemist, Marie Curie, from Poland, working in Paris, France. She used the same type of rock that Becquerel did, and she discovered other radioactive materials, radium and polonium, byproducts of uranium, as well as radon gas inside that same rock. So we now know that uranium atoms disintegrate slowly, giving off what's called ionizing radiation. Those are those tracks that you were seeing in the cloud chamber. And when it gives off one of these bursts of energy, the atom of uranium changes into a different kind of atom. It changes into a series, in fact, of other unstable elements. And so we have not just one radioactive material, but a dozen or 2 dozen radioactive materials in the same rock, all byproducts of uranium. Now, there are 4 types of emissions that radioactive material can give off: alpha, beta, gamma, and neutron radiation. Gamma radiation is the only one that's really a ray, like light waves or heat waves or infrared or ultraviolet. Gamma rays are in that same spectrum of energy. But the other things, alpha, beta, and neutron radiation, are not really radiation at all. They're particles. They're 2 of them are charged particles, the alpha and the beta. The neutron is not charged. And they are all, the gamma, the alpha, the beta, and the neutron, they're all damaging to living cells because they're ionizing energy. That means that they break chemical bonds randomly. And this creates havoc in a cell or in any other kind of material and causes random chemical reactions to occur that normally would not occur without the influence of this ionizing energy. So that's where the damage to living cells takes place. Once a cell is damaged, it can grow in an abnormal way, and it can become a cancerous growth, or it can become a genetic abnormality if it's a reproductive cell, or it can become some other kind of source of illness. The alpha radiation won't even penetrate through a piece of paper, the alpha particles. The beta particles are more penetrating, but they won't even go completely through a hand. Gamma radiation is more penetrating. It'll go right through your body and it'll be partway through concrete. Neutrons are also very highly penetrating. They're not stopped by steel even, but they can be stopped by concrete. So they have different degrees of penetration. And the surprising thing is that the less penetrating forms of radiation, alpha and beta, once they're inside the body, they're actually the most dangerous. They're the ones that do the most damage. In fact, it turns out that the alpha particles, once they're inside the body and in contact with living cells, they're hundreds to thousands of times more damaging per disintegration than gamma rays or beta rays. Now, radium that Marie Curie discovered in the rock, she realized that the harmful effects of atomic radiation can be used to destroy tumors. So she started using radium needles. And the idea was that you could take a malignant growth or even a non-malignant growth and stick one of these radium needles into it. And the radiation, if it can burn human flesh the way it did with Henri Becquerel's chest, surely it can do the same thing to a tumor. And so this became a standard way of treating solid tumors for about 20 years, from 1905, 1910 onwards. And unfortunately, radium was also used for other more frivolous reasons, which aren't such a good idea. For example, a lot of young girls were hired, thousands of young girls were hired to use a radium-based paint to make numerals or watch dials and instrument dials glow in the dark. They ingested minute amounts of radium when they licked the tips of their brushes to get a very fine point. And they died from terrible diseases, one of them being fatal anemia, another being bone cancer, another being head cancers. And it's a tragedy, and everybody knows about it. And this took place and became unveiled in the 1920s. So it's been known for a very long time. And by the way, when these girls died, they did autopsies and they found out that the maximum amount of radium in the body of any one of these dead girls was only 18 micrograms. That's a millionth of a gram of radium. 18 micrograms is 55 times smaller than the finest particle of sand you could ever imagine. So if you look at the size of sand particles, the finest ones, 55 times less than that is how much killed these girls. So it's very difficult to wrap your mind around how very powerful the nuclear energy is that comes from the nucleus of the atom, and therefore how very powerful atomic radiation can be. Polonium is another substance that Marie Curie discovered in the same rock. And it turns out that it was used to murder a man named Alexander Litvinenko in London, England in 2006 by just putting a drop of polonium-210 into his tea. Los Alamos Nuclear Laboratory says that polonium is 250 billion times more toxic than hydrogen cyanide, one of the deadliest fast-acting poisons we know chemically. So very hard to wrap your mind around that. But this polonium attaches itself to the red blood cells and gradually knocks out the soft organs one after the other. Took him about 30 days to die, and it was a terrible death. He had to be buried in a lead-lined coffin because of the radioactivity of the corpse. This is a underground miner, a Navajo Indian miner with lung cancer. He was a non-smoker. In fact, all the Navajos were non-smokers. None of them smoked. And his wife is standing beside him. He died a few months after this picture was taken by my friend Robert Del Tredici. And he died by breathing a radioactive gas called radon gas. It's produced when the radium atoms disintegrate. The radium is actually a metal, but it's radioactive. And when the atoms disintegrate and give off those particles, they change into a different substance, and it's a gas. It's called radon gas. Radon gas is also radioactive, and when it disintegrates, it turns back into a solid called polonium. That's where the polonium comes from. So all these things are interrelated, and it makes it difficult for ordinary people who aren't scientifically trained to understand the kind of transformations that radioactive materials undergo and how things can become so different from each other and yet so dangerous. Radon is the leading cause of lung cancer among non-smokers. This is universally acknowledged. It causes lung cancers and other lung diseases in uranium miners. And it also, as it migrates through the air, it deposits solid radioactive materials not only in the lung tissue if you inhale it, but also onto the ground below. It's called radioactive fallout from the radon gas. Radon is 7 times heavier than air, and it travels great distances in a light breeze. Here's a picture through a microscope. It's a slice of lung tissue from an experimental animal, an ape, and you see a particle there, radioactive particle, that emits alpha particles. It could be a particle of uranium, but in fact, in this case, it's a particle of plutonium, a tiny little speck of plutonium. And those spikes that come out from it, this is filmed over a period of 48 hours. So those spikes that you see are actually the tracks of the alpha particles that are given off in a 48-hour period. You'll notice that they don't go very far because they're particles which are quite heavy, and but they do damage the cells that are close by. And once those cells get damaged, they can then develop into a cancer, which could manifest into a full-blown lung cancer 20 or 30 or 40 years later. So there's a latency period, which means there's a delay between the radioactive damage and the development of clinically observable illness. By the way, all of these deadly radionuclides that I've been talking about, radium, radon, and polonium, they're all alpha emitters. They all give off alpha particles. They're harmless outside the body, but deadly inside the body. Uranium, thorium, and plutonium are also alpha emitters. So don't let anybody tell you that if something doesn't register on a Geiger counter, it's not dangerous. That's not true. These things generally do not register on a Geiger counter because they don't have a long enough track. But they're very, very dangerous inside the body. Because so far, what we've been talking about is things that happened in other countries. But Canada got into this in 1931. In fact, there was a company called Eldorado Gold Mine Company, and they discovered a cache, a deposit of radium, a rich deposit, way up in the north of Canada, on the shore of Great Bear Lake, which is only about 100 kilometers south of the Arctic Circle. They hired a student of Marie Curie's to design what's called a radium refinery in order to extract the radium from the ore. Now, why would they be extracting the radium? Well, that's because the price of uranium at that time was about $70,000 a gram. So it was one of the most valuable substances on Earth. After a while, as a matter of fact, over the decade from 1930 to 1940, the price dropped from $70,000 a gram to $40,000 a gram, whereupon the whole operation shut down, partly because the price had dropped so much, and also because of the outbreak of World War II. What you're seeing here is the harbor and marina at Port Hope, Ontario, with the uranium conversion facility in the background, which is, this is a modern picture. It's no longer a radium refinery. It's a uranium processing conversion plant. Where Port Hope got its radium ore was, as I said, way up in the Northwest Territories on the shore of Great Bear Lake, a territory that was occupied for thousands of years by the Satu Dene indigenous people. They have a community up there called Delaney, which is across the lake from where the mine is. Port Radium, where the mine is on the east shore of Great Bear Lake. Delaney is now known as the Village of Widows because so many men have died of various forms of cancer, almost certainly because of their handling of radioactive ore. They were actually paid the equivalent of about $1 a day and they actually called them coolies. They called them coolies, and they hired them to carry the sacks of radioactive ore on their backs. They were never told that the stuff is dangerous. They were never given advice to, if one of the bags ripped open and they were covered with yellow powder, to wash it off as quickly as they could and make sure it didn't get into their lungs or their ears or their hair or their body. They were never told any of this. For them, it was just a job carrying these sacks. Also, they had to put the sacks on a barge, which took about 8 hours to cross the lake, and they would often sleep on the sacks as it crossed the lake. So here's a man, a Dene man, standing over discarded uranium ore sacks at Port Radium, Northwest Territories. Because they were never told that these sacks were dangerous, the women would gather these sacks not to be wasteful and take them home with them to reuse them, because waste not, want not, right? Unfortunately, they were carrying into their homes this deadly material, radium, which gives off the deadly radon gas, which in turn produces polonium. So all of these radioactive materials that Marie Curie discovered were being carried into the homes of the Dene people and causing a lot of harm. These two Dene men are holding something which I will show you in the next slide. It's a publication from the Canadian Department of Mines, dated 1931. And here's what it says. It says that the hazards involved in the handling of high-grade radioactive materials makes necessary the adoption of certain precautions. Lung cancer, bone necrosis, and rapid anemia are possible diseases due to deposition of radioactive substances in the cell tissue or bone structure of the body. Now, this is 1931. That's long before the first nuclear reactors were ever built. And they knew this because of the radium dial painters and because of the underground miners who had been dying. So by 1931, it was well known that this material is very dangerous in very tiny amounts, and that it causes cancers and it causes anemia, blood diseases. By the way, Both Marie Curie and her daughter Irene Curie died of rapid anemia. Now, the harmful effects of ionizing radiation are now known. We knew, of course, right from the beginning that acute exposure causes radiation burns, Becquerel, for example, and can even be deadly. Chronic exposure increases the incidence of cancer, leukemia, and genetic damage. That's damage to the reproductive materials, as well as strokes, heart attacks, and lowered intelligence. Now, those last three things, strokes, heart attacks, and lowered intelligence, those were not known in the early days. They have become known more recently. But we did know about the cancer, the leukemia, and the genetic damage way before the first nuclear reactors were ever built. And for cancer, we also know that there's a latency period. The onset of disease occurs years or even decades after exposure. So moving to part two now, materials for nuclear weapons, 25 years of activity, more than 25 years, where Canada played an important role. Now, uranium turns out to be the key element in all nuclear fission technology. I'll explain what nuclear fission is in a moment. Without uranium, there would be no nuclear weapons of any description, and there would be no nuclear reactors of any description. As a result, some people, including my organization, have urged that this stuff should be left in the ground and should not be mined. There are very few substances that are so dangerous that they should not ever be mined. One of those is asbestos, because the dangers of asbestos far exceed the advantages. And another one is uranium. So, of course, this is a matter of great contention and disagreement, but all uranium that's mined either is used for nuclear weapons or it's used for nuclear reactors. So it all turns into either bombs, which are enormously destructive, or radioactive waste, which is extremely dangerous for a very long period of time. So what is nuclear fission? What is this fission business? It turns out that in 1938, around Christmas time in 1938, a subatomic projectile called a neutron was discovered to start a nuclear chain reaction when it hits a nucleus of a fissile uranium atom. That's a rare kind of uranium called uranium-235. It's only 7 atoms out of 1,000. When you mine uranium out of the ground, only 7 atoms out of 1,000 are uranium-235. The other types of uranium are non-chain reacting. They don't undergo the nuclear fission chain reaction. But uranium-235 does, and when the neutron is absorbed, the atom actually splits. It's called splitting the atom. And the results are smaller atoms, 2 smaller atoms, which are intensely radioactive. These are new radioactive materials that were never found in nature before 1940. So these fission, they're called fission products. So these new fission products, and there's hundreds of varieties of them. And at the moment that the atom is split, a great deal of energy is released. And now, that amount of energy would not even be enough to heat your tea unless you could multiply it. And it turns out that when the atom is split, it gives off more neutrons. And those more neutrons can trigger more fissions. And in that way, you can get a chain reaction. If you have a lot of U-235 together in the same place at the same time, you can get a chain reaction that will give off more and more and more energy. And the problem is not how much energy it gives off, but how to control it to make sure it doesn't get out of hand. And therefore, you have very serious control mechanisms to make sure that those neutrons don't produce an explosion. But they do go on to produce more radioactive byproducts besides the fission products. One of the things they produce is a substance called plutonium. Now, the creation of plutonium in a nuclear reactor, I told you that the U-235, when it splits, it gives off the fission products. Well, there's another type of uranium, uranium-238, much more abundant. And when it's struck by a neutron, instead of splitting, most of the time it creates a heavier element called plutonium, plutonium-239, which is produced from uranium-238 by absorbing a neutron. Now that plutonium, it turns out, is a very powerful nuclear explosive, even more powerful than uranium-235. And it can be used either as fuel for nuclear reactors, or it can be used for nuclear weapons now, or many thousands of years from now. Why is that? Well, it turns out the plutonium has a long half-life, 24,000-year half-life. That means you've got to wait 24,000 years for half of the plutonium atoms to disintegrate. That means that 10,000 years from now, there's lots of plutonium still there in the irradiated nuclear fuel. And anybody can come and get it out and use it to make bombs. So you can make bombs from this material thousands of years from now. Plutonium does not exist in nature. So when you go looking for it in nature, you don't find it. Where you find it is where you have operated nuclear reactors and produced a stash of spent nuclear fuel, used nuclear fuel, which contains that plutonium as well as the fission products. Now, that's what made Canada important back in 1943, during the height of World War II. In Quebec City, Prime Minister of Canada, Mackenzie King, played host to President Theodore Roosevelt from the USA and Prime Minister Churchill from Britain. And they signed a secret accord called the Quebec Accord. And the Quebec Accord was a tripartite agreement for these three countries to cooperate in building the world's first atomic bombs. Why Canada was important is because Canada had that radium mine, which also is a uranium mine. Because remember, radium is only created by the disintegration of uranium. So wherever there's radium, there's got to be uranium also. That's how they knew that Canada had a lot of uranium, and we should be able to access it pretty easily for the bomb program. In fact, there were two bombs that were used in warfare. Little Boy is the name of the bomb that was dropped on the city of Hiroshima in August 6, 1945, and that was a uranium bomb. The other bomb is called Fat Man, and it was dropped on Nagasaki 3 days later on August 9th, 1945, and that bomb was made of plutonium. However, don't forget, plutonium is a uranium derivative, so you wouldn't have any plutonium if you didn't start off with uranium. This is what happened to a single uranium bomb, Little Boy, dropped on the city of Hiroshima. It wasn't actually dropped on the city. It was exploded in the air because they didn't want to create a crater. They wanted to study the damage and the effects of radiation. A blinding flash of light is so intense that it will burn the retinas of anybody who happens to be looking in that direction. And it will also, it sends out an enormous wave of heat that ignites everything that's flammable within several kilometers. So that everything that is burnable burns. And of course, there's the blast, which destroys the buildings. And there's also the radioactive fallout, most of which went into the stratosphere because it wasn't, as I say, it wasn't exploded at ground level. It was exploded in the air above the ground. Now, Canada became important as the supplier of uranium, not only for the Manhattan Project, which was, of course, ended in 1945 with the dropping of the atomic bombs, but then there was the Cold War, in which tens of thousands of nuclear weapons were built up in the United States of America, and Canada was the major supplier of uranium. All these mines were built, at least most of these mines, not all of them perhaps, were built to service the US military machine and provide uranium for bombs. So tens of thousands of nuclear warheads in the United States. Most of them probably have a little bit of Canada in them. Here's a list of the mills where they crushed the ore to get the uranium out, and which mills were used for bombs and which mills were used for nuclear power. The cylindrical things on the left are called fuel bundles for CANDU reactors, and the drums on the right are called hex for hexafluoride, uranium hexafluoride. 85% of our uranium from Canada is still exported overseas, and only about 15% is used domestically. Now, when you mine uranium, you're not just mining uranium, you're actually mining a whole lot of radioactive materials, all of the decay products, they're called. Because remember, as I told you, when uranium atoms disintegrate, they don't turn directly into radium, they turn into something called thorium-234. And that's radioactive. And then when it disintegrates, it turns into protactinium-234, and so on and so on. But on that list, you have the radon, the polonium, the radium, and many other materials as well. And when you mine the uranium, you only take off the top part and you remove that. 85% of the radioactivity in the ore stays behind as sand-like radioactive mill tailings with an effective half-life of 76,000 years. And by the way, all of these materials that I've shown in this picture, they're all far more dangerous, far more toxic, you might, if you put it that way, than uranium itself. So these are the worst of the worst. Radium is there, radon is there, polonium is there, and other things as well. So all of the radium, radon, and polonium is discarded as waste and will be a hazard to health and the environment for many thousands of years to come. We have now in Canada approximately 230 million tons of radioactive sand left over from uranium mining. This is a wall of such radioactive waste, 30 feet high, that's 10 meters high, 10 meters high, and behind that wall is an entire lake full of this same material. It's all radioactive waste. It's all radioactive waste left over from uranium mining. And it's in the Elliott Lake area of Ontario, and it'll be there for thousands and thousands and thousands of years. And it's so fine that it easily drifts into the environment, is washed into the environment. So you have to do some pretty serious things to try and keep it from contaminating the environment for thousands of years to come. People wonder whether what we're doing right now to contain this waste is at all adequate for the many generations, the thousands and hundreds of thousands of generations to follow us. The hazards from mill tailings are not only the gamma radiation that they do give off. So if you were, for example, to have a picnic or fall asleep on uranium tailings pile, which people do, you get gamma radiation. But there's also radon gas coming off all the time. There's also dust blowing in the air, which includes radium, so it's spreading radium around. And there's also seepage into the groundwater. So it's a multifaceted environmental hazard. Now, Port Hope itself has also been undergoing a $2.6 billion radioactive cleanup, which started back in 1975 and is still going on. And in fact, it will continue to go on. They just got another 20-year license, and they're spending billions of dollars cleaning up the radioactive sand that they used as building materials around town. They actually used it to build homes, schools, buildings of other kinds. They also dumped it into the harbor. They dumped it into ravines. They dumped it into the sandy beach, the public beach, and so on. And it wasn't because they didn't know better, because in fact they did. Now, I've shown you these slides before, so I won't repeat them, but I will say this, is that in addition to the legacy of uranium mining, there's also the legacy of plutonium production. At Chalk River, Ontario, we have a plaque that has since been removed, but my friend Bob took a picture of this. The ZEEP reactor, the very first reactor that Canada ever built, started operation just 1 month after the bombing of Hiroshima. And that's because it was already under construction even before the bomb was dropped, because Canada, being a member of the Quebec Accord, had to be notified when the bomb was going to be used. Now, what the plaque says is that the ZEEP reactor started up in September 5th, 1945. It was originally part of an effort to produce plutonium for nuclear weapons. As a matter of fact, the first reactors that were built solely for the purpose of producing plutonium for nuclear weapons. And in fact, Chalk River continued to produce plutonium not only in this reactor, but in several other reactors. And they sold plutonium to the US military for bombs until 1965. Chalk River operated also on their site of Chalk River, right beside the Ottawa River, above the nation's capital. They operated 2 reprocessing plants. Now, what is a reprocessing plant? Well, that's a plant to extract the weapons usable materials from the irradiated fuel rods or target rods that are used in the reactor. So, and that means you have to separate the plutonium and other materials from the fission products, which are intensely radioactive and very dangerous. So that's what a reprocessing plant is. And the leftovers of a reprocessing plant are very difficult to deal with. Now, this glass ball is exactly the same size as the ball of plutonium in the bomb that destroyed the city of Nagasaki. That's how much plutonium you need to destroy a city. And that's what we were producing and selling to the American military. We sold about 245 kilograms of plutonium to the American military over that period of time. Now, here's a picture of Howard Moreland. Howard Moreland is a journalist, and he wrote an article called "How to Make an H Bomb." And uh, and because of that, he was sued and had to go to the Supreme Court. But he won his case because he was able to show that everything he wrote in his article was already in the Encyclopedia Americana under the byline of Edward Teller, the so-called father of the H-bomb. So none of the material was secret material. It was all publicly available. And you notice that right at the top of the H-bomb, that's a hydrogen bomb, much more powerful than an atomic bomb. But even the H-bomb requires plutonium. If you take the plutonium out of the H-bomb, it's not a bomb anymore. It can't be used. And in fact, when they dismantle H-bombs, when they dismantle strategic nuclear warheads, that's exactly what they do. They take the plutonium out. The question then, of course, is what do you do with it? Now, reprocessing, as I mentioned earlier, is a way of separating plutonium from the spent fuel. If you don't separate the plutonium, then you have a firewall between the used reactor fuel and the possibility of using it for bombs, because the irradiated fuel is simply too radioactive to be handled without heavy shielding. It'll kill anybody who tries to handle it. In fact, a human being would die in about 20 seconds by just standing 1 meter away from a freshly irradiated nuclear fuel bundle. So that's why we can have some assurance that in most nuclear reactors, there's no bomb making going on. But if you build a reprocessing plant, that's a commercial facility which actually separates the plutonium from the highly radioactive fission products. Once it's separated, then it can go anywhere. It can go out the front door as fuel for another reactor, or it can go out the back door and be used for bombs. So this is why reprocessing is considered a very dangerous process from national security point of view. In fact, that's why Jimmy Carter, President Jimmy Carter, banned plutonium reprocessing back in 1977 in the United States, a ban which has subsequently been reversed. But I would like everybody to realize that when you hear the word reprocessing, they don't use that word so much anymore. They call it recycling nuclear waste. When you hear about recycling nuclear waste, beware. What they're really talking about is extracting plutonium, and that creates a huge problem because even if you have no evil intentions with the plutonium, other people do, and they can steal that plutonium once it's separated and even carry it and smuggle it across borders without much fear of detection. And then they can be criminal organizations or terrorist organizations can use that material to make homemade atomic bombs, improvised atomic bombs. This is the waste that's left over from reprocessing at Hanford, Washington. Millions of gallons of high-level liquid waste are stored in tanks. Those liquid wastes are extremely radioactive and will be dangerous for a very long time because the nuclear waste is left behind. So moving to part 3 now. Part 3 is about nuclear power and the CANDU reactor. I'm just going to go through this part pretty quickly. A CANDU nuclear reactor works as follows. We put uranium in the core of the reactor. That's that yellow square area there. And there we have a fission chain reaction going on, which is used for one purpose only, and that is simply to boil a lot of water. And that's what it is. It's simply another way of boiling water. And that water creates steam. The steam is then used to turn a turbine and generate electricity. Once the water is boiled, it's no different from a coal-fired plant, an oil-fired plant, or any other wood chip-fired plant, whatever. It's just how you boil the water. The problem is, however, that in splitting the uranium atoms, you create all this radioactive garbage, which is going to remain dangerous for tens of millions of years. Now, here we have a picture of CANDU fuel bundles. These are mock, of course. This is an actor in an ad called Small Wonder from the Canadian Nuclear Association. He's saying, isn't it wonderful how much this little pellet of uranium can supply as much energy as a carload of coal? But what he doesn't tell you is that once that fuel pellet has been used to produce energy, you can't throw it away. You have to keep an eye on it for the next 10 or 20 million years because it has become one of the most dangerous objects on Earth due to the production of fission products inside. So a CANDU fuel bundle can be handled safely before it's used, but after use, the gamma radiation will kill any human being in less than a minute. This is from the Royal Commission on Electric Power Planning report of 1978. The extreme lethality of a freshly removed spent fuel bundle is such that a person standing within a meter of it would die within an hour. It looks solid, but radioactive materials leak out through tiny pinholes and cracks. Severe fuel damage causes massive leaks. Fuel suffers corrosion, distortion, and embrittlement in the reactor. And as a result of that, all of the piping system in the reactor becomes radioactive because of small leakages from these fuel bundles. Here's what the face of a CANDU reactor looks like. It's got hundreds of horizontal fuel channels. This is the face of the Darlington reactor before it ever started up. If it had been started up at any time, this man who's standing there would be dead because the radiation from the fission products would kill him in very short order. So we built a lot of reactors in Canada, and here's a list of them. The Pickering A, Pickering B, Bruce A, Bruce B, and Darlington are all units of 4 reactors each. So that's 4, 8, 12, 16, 20 fuels right there. And then we've got other reactors as well. So we have about 25 reactors, let's say, which are power reactors. We're not counting the smaller research reactors, such as the NRX and the NRU. Those are reactors that don't produce electricity, but produce other things. They can produce plutonium, or they can produce medical isotopes, or they can produce various other things as well. We also exported to many countries. India, originally, 1964 is when we started exporting reactors to India. But in 1974, India used the plutonium from a Canadian reactor to make an atomic bomb. And after that, we stopped selling them any nuclear equipment, kind of like shutting the barn door after the horses escaped, of course. But we still sell them uranium. It's amazing. We just sold them $2.6 billion worth of uranium, which is kind of crazy because even if the uranium is not used for bombs, it'll free up other uranium that they have that they can then use for bombs that they would otherwise have to use for the reactor's fuel. So we're helping them build bombs, even though we don't think we are. And Pakistan, Korea, Argentina, Romania, China, these are the countries that we've sold nuclear reactors to. In 1978, the whole construction era of nuclear reactors in Canada came to a halt, partly as a result of a 1978 report called A Race Against Time. And one of the things that that report said is that if you don't solve the waste problem, you have to stop building more nuclear reactors. This is the Royal Commission on Electric Power Planning, and I played a significant role in that report, cross-examining nuclear experts on a daily basis for over 3 months. This is also from the same report, and it shows the toxicity of radioactive waste. The blue line at the top is the toxicity. That means how much it would be harmful to people if they got it into their bodies. And that's for total high-level radioactive waste. At the very top left, you notice that you have the volume of Lake Superior. What we're talking about here is how much water you need to dissolve this waste to the maximum level permitted by law for drinkable water. And the chart actually deals with the nuclear waste from only one nuclear reactor for only 1 year. So this is 1 year's worth of nuclear waste from one nuclear reactor. And the question is, how much water would you need to dissolve that waste to the maximum level of contamination permitted by law? And the answer is, it's about the volume of Lake Superior. So when you look at that, you say, wow, how many Lake Superiors do we have? If you had, let's say, 20 reactors, each operating for 30 years, that's 600. We don't have 600 Lake Superiors, which explains why people are so tense about what to do with this waste. You got to have real perfection in storing this waste and keeping it out of the environment. You can't allow 1% of it, or even 0.1%, or even 0.01%. to escape. And here we have in 1978, in fact, they started looking at the so-called geologic disposal concept for used nuclear fuel. Maybe if we bury it deep enough underground, it'll never come back to hurt us. And they built, in fact, an underground research laboratory in Lac du Bonnet, Manitoba, near Lac du Bonnet in Manitoba. And surprisingly enough, they didn't put any waste down there. They just wanted to study the rock and see if it was suitable. But Manitoba, in fact, turned around and passed a law making it impossible for them to bury any radioactive waste in Manitoba. So that law is still on the books today. Now, part four is the nuclear stagnation, which set in after 1978. No more reactors were built in Canada, and even overseas sales were skimpy. And that lasted at least until 2018. There still haven't been any new nuclear reactors built in Canada, but there's one under construction, and that's the so-called small modular reactor at Darlington, Ontario. During that time, I wrote a number of papers, and many other people wrote papers about the cost disadvantages of expanding the nuclear power industry. And one such article, quite a long one I wrote, is called Canada's Nuclear Dilemma. And the question is what to do with the nuclear industry if we don't have any customers. And we still, to this day, really don't have much in the way of customers. We've got a few, but very few. There are good economic reasons to think that we should just say, well, it was fun while it lasted, but it's over. The atomic age is now past, and we don't need any more. We also see hopium at work. I call it hopium on steroids. If you look at the figure on the left, this is in one of my papers. It shows predictions made by Atomic Energy of Canada Limited, AECL, and Energy Mines and Resources as to how much nuclear power we would have by the year 2000. And you notice they were predicting that you would have way over 100,000 megawatts of nuclear power, maybe even as much as 130,000 megawatts of nuclear power by the year 2000. Those projections, as the years unfolded, gradually diminished until they got down by 1979. They were down to predicting only 26,240 megawatts. But you know what? Even that is way too much because, in fact, we have less than the confirmed amount they have at the left there, 15,190 megawatts. That's more than we have right now because we've shut down the 4 Pickering reactors permanently, the 4 Pickering A reactors. So we have actually less than that. We only have a little bit more than maybe 12,000 megawatts, and that's what we have at the moment. So there were also nuclear safety concerns. This is something many of you might not have heard of, but back in 1997, the board of directors of Ontario Hydro became so concerned because they couldn't understand what they were being told by the nuclear department. And so they hired outside experts to come into Canada from outside, from the United States, and do a report card on the nuclear safety of Canada's nuclear reactors. That report card was so alarming, saying that Ontario's reactors are minimally acceptable in the safety domain, so that the board of directors immediately shut down 8 of Canada's nuclear reactors in Ontario. And those remained shut down for 6 years. From 1997 to 2003. That's the 4 Pickering A reactors and the 4 Bruce A reactors. When they tried to restart them in the 21st century, they got 2 of the Pickering units restarted at an exorbitant cost, way more expensive than anybody expected. And so the other 2 were simply written off. Now all 4 of the Pickering A reactors are permanently shut down. And they're now talking about fixing, refurbishing, they call it, the other 4 reactors, the Pickering B reactors. I won't go into the saga of the Slowpoke 3. It was a district heating reactor, a kind of a small modular reactor that Atomic Energy of Canada Limited was trying to give away free of charge to the University of Sherbrooke, who needed a new heating system. They accepted this gift, and then 1 year later they said, no, we reject it because they found out the truth. They were not being told the truth about what type of machine this was, this nuclear reactor. Once they started learning what it was and the waste that it produced and so on, they said, thank you, but no thank you. By the way, AECL then went to Saskatoon, Saskatchewan and tried the same thing there. and it was rejected out of hand based on the Quebec experience. So it was planned as a demonstration reactor in Manitoba on an Atomic Energy of Canada Limited site, but it was judged to be too unsafe to be licensed for operation. So the whole idea was dropped. That's only one of several examples of how the nuclear industry in Canada tried to get something happening, tried to get something going to get out of the stagnation they were in. They also tried to build two reactors called the Maple reactors, Maple 1 and Maple 2, each one only 10 megawatts. They couldn't get those working either. And those reactors are now slated to be decommissioned without ever having done any useful work at all. But this is global. In 2019, it was revealed that there had been stagnation globally in the nuclear industry for about 25 years. For example, in 1996, there were 438 reactors representing about 17% of global electricity. But in 2019, there were only 442 reactors. That's only four more in 25 years. And it represented only 10% of global electricity. So it's now down to 9%. So the actual market share of nuclear electricity is dropping rapidly and has been for about 25 years. The state of affairs in 2019, I'm picky on 2019 because that's when Canada tried to step in, the Canadian government tried to step in and revitalize the nuclear industry in Canada. So in 2019, the American Society of Mechanical Engineers, called ASME, said that the most optimistic global electricity market share for nuclear was only about 5%, down from 10% today. And in the United States and Europe, it steadily declines to between 3 and 5% of the market, constituting a potential for market failure. That means that they've priced themselves right out of the market altogether. So you can see that the nuclear industry was in very dire straits and still is, by the way. So the first nuclear renaissance took place around 2001, but it turned out it didn't work very well. A French giant company called Areva went bankrupt in that period of time based on an Olkiluoto reactor they were building in Finland. It started construction in 2005. It was supposed to take 3 years to build, and it cost 3 billion euros to build. It turns out that it didn't start up until March 2022, 19 years later, at a cost of more than 11 billion euros. So it took 6 times longer to build than promised and cost 4 times more money. The bankruptcy of Westinghouse was in 2017. It was also based on huge losses. Westinghouse Electric filed for bankruptcy with $9 billion in losses from new nuclear projects, mainly the 4 AP1000 reactors, Vogtle in Georgia and VC Summer in South Carolina. South Carolina abandoned the project. Georgia did not. The U.S. government gave $8.3 billion in loan guarantees on the financing of the 4 reactors, but it turns out that the estimated cost of $14 billion, actually turned out to be 35 to 36 billion. The estimated time of completion was supposed to be 2016 or 17. Actual completion was 2023 or 24. So it cost more than doubled, and the time to build tripled. And the cost per kilowatt installed is now, in US dollars, $15,700 per kilowatt. That's the costliest electricity capacity in the entire world. In 2023, Westinghouse was bought, so it came out of bankruptcy, by 2 Canadian firms, Cameco, that's the uranium giant from Saskatchewan, who owns 49% of it, and Brookfield Financial, which was at that moment under the guidance of our Prime Minister, Mark Carney, which owns 51%. So these 2 Canadian companies bought Westinghouse, and it's now an American company that is Canadian owned. Part 5, small modular nuclear reactors. As I said, in 2018, Canada started promoting small modular nuclear reactors. They regard it as a kind of a second nuclear renaissance, and they dropped out the letter N. They call it SMRs instead of SMNRs, because nuclear is really the problem. If you don't have the N there, you don't have any problem. Unfortunately, the N can be taken out of the word, but it can't be taken out of reality. So SMR could also be regarded as a second make-believe renaissance. I call it that because in the whole Western world, despite 8 years of hype, there isn't a single small modular reactor in operation anywhere in the Western world, although there is one under construction in Ontario at Darlington site. The problems with these small modular nuclear reactors is they're very costly. You need mass production to overcome the cost differential. The problem is that when you make a smaller reactor, it's less efficient, and you end up having to spend more money per kilowatt than you do for a large reactor. That's why they moved to the large reactors in the first place. Also, there's too much competition. There's too many different models. There's 150 different models at the present time. That makes it impossible to standardize, and that makes it impossible to really move to mass production. You can't mass produce something if you're not going to have at least a few hundred orders, or maybe better, a few thousand orders. So it's also very hard to find private funding. Public money is easier to come by, and that's why they are robbing the Canadian Treasury and the American Treasury to get these projects started. There isn't any private money that will do it. There's also very few markets, very slow deployment, and these devices, once they're built, they're more vulnerable to external threats like earthquakes and hurricanes and war because they're less robust. They're smaller and they don't have those huge, thick concrete walls that most reactors do have, the old ones. So in short, they're not so small, they're not so modular, they're not so affordable. They are, however, nuclear. So there are many things that they claim to be, but they're not. And one thing that they claim not to be, but they are. They are SMNRs, not SMRs. Here's some examples. In Idaho, this project was canceled in 2023 when the price of the projected power doubled. The clients backed out. Here's another one at Chalk River, Ontario. It's supposed to be only 5 megawatts of heat. 5 megawatts of heat, that's very little. And yet, the ultra-safe company filed for bankruptcy in 2024. And so this project is paused. It's not canceled. It's intended for the Chalk River site in Ontario, but they have nobody yet at the moment ready to build it. Here's the one they are building at Darlington. The BWRX is a boiling water reactor, 300 megawatts. They call it a small modular reactor, but it's estimated to cost $6.5 billion for Canadian money. That's really, as I will show in a moment, it's about equal to the cost per megawatt of the Vogtle plant in Georgia that I mentioned a few slides back. It's under construction. The Canadian regulator has given a construction license for the first of 4 units to be built east of Toronto. But if you look closer, you've revealed that the BWRX is actually 21 stories high. It's 10 stories above ground, another 11 stories below ground. So it's not so small. They build it that way to try and deceive your eye, but it's also not so modular because a workforce of up to 4,000 has been cited by the Prime Minister, who has invested federal money in it, a couple of $1 billion into this, even though it's a provincial project. And here, by the way, is the site. This is where you see that crane that is lifting that concrete slab? That is the largest crawler crane in the entire world. It's needed to lift the concrete foundation of the BWRX, which is going to be underground, and it has to lift it up and drop it down that cylindrical hole to the bottom. That's going to be the base of the reactor. And you look at those little dots around the roads, those are cars and trucks. So you can see that this is really the size of a mall with the lead time of a cathedral. And it's not, not anything that most of us would call small. License to prepare the site was given to OPG way back in 2011. And now they're just going ahead now to start building it. And by the way, it's only 3% of the Wesleyville project, which I'll mention in a few moments. This is 300 megawatts. The Wesleyville project, which is being proposed, is 10,000 megawatts, which is 97% larger than this one. The cost of the first 300 megawatt unit is 6.5 billion. That means the cost per kilowatt, you just divide 6.5 billion, just simply divide it by 300 megawatts, and you get 21,666 Canadian dollars per kilowatt. That translates to 15,500 US dollars per kilowatt, which corresponds pretty closely to the total cost, 15,700 US dollars. Very expensive electricity, which might explain, by the way, and the way they made it smaller was by eliminating a bunch of safety systems, which is very perturbing. They got rid of the emergency core cooling system. They got rid of the core catcher in case the core melts down. They got rid of the emergency relief valves, pressure relief valves in the primary core. So they got rid of a lot of safety systems in order to try and make it smaller and more affordable. So part 6, and this will be the end of my talk, Back to the Future, nuclear expansion from 2024 to 2050. I go to 2050 because that's what they're thinking about. The new nuclear plants are not small at all. It's as if they've given up on the small modular reactors already. There are new large nuclear power plants being proposed in Canada right now. The Peace River new nuclear project is 4,800 megawatts, 4 large reactors, each of about 1,200 megawatts. The Bruce C new nuclear, which is, by the way, the Peace River new nuclear is on the Peace River, of course, flowing into the Peace River Athabasca water basin, one of the largest freshwater, the outflow in the world. The Bruce C new nuclear is also 4,800 megawatts. That's planned for Lake Huron. The Wesleyville new nuclear is supposed to be 10,000 megawatts. That would make it the largest nuclear plant in the entire world. And these would be all large nuclear reactors. So the total for large nuclear plants being proposed is 19,600 megawatts. They're not small modular reactors. They're all big ones. The plans for new small nuclear plants in Canada is only 4 BWRX-300s at Darlington. That's 1,200 megawatts. 1 ARC-100 at Point Lepreau. That adds up to 1,300 megawatts. Nothing. It's a drop in the bucket compared with the large nuclear plants. So the large nuclear power plants that are planned in Canada are 15 times greater and vastly expensive, hundreds of billions of dollars, much greater than the SMR plans. So was the promise of SMRs just a way of rehabilitating nuclear, just a way to get people to think, nuclear hopium? Getting people to think that nuclear has been rehabilitated. Now it's safe. Now it's clean. Now it can be thought of as desirable, whereas we didn't think so just a few years ago. Here is the site for the Wesleyville project, and what they want to put there is something about twice as big as this. This is the Bruce site in Ontario, Canada. If you imagine something almost twice as much as that, that's what they're planning for the Wesleyville project, just outside of Port Hope, right on the north shore of Lake Ontario. Now, and by the way, Bruce Power requires extraordinary security. They have a SWAT team that is permitted to use prohibited weapons. Those are fully automatic rifles that act like machine guns. They have won U.S. National SWAT Championship competitions multiple times. They're really tough. And so that's what you're going to need at these new large nuclear facilities. Despite the fact that they are called safe, you have to spend a lot of money on weaponry and preparedness to try and make them safe. And the competition, of course, is renewable energy, and the renewable energy is, it turns out, a whole lot cheaper than nuclear. Here in this graph, the money goes from left to right, it gets more expensive as you go from left to right. So you can see that the solar, even with storage, and the wind also with storage, even at the highest, most costly end on the right-hand side, is cheaper than the cheapest nuclear. So the cheapest nuclear is a lot more expensive than the most expensive wind or solar. So the question, of course, is how come we're not spending our money on what is cheaper and faster rather than on what is more expensive and slower? In the international conference called COP28 back in 2023, over 200 nations pledged officially to try and triple renewable energy by 2030 and double energy efficiency also by 2030, which is considered to be difficult but not impossible. On the other hand, about 25 other nations, including Canada, took an unofficial oath that they would like to triple nuclear power by 2050. Please notice that's 20 years later than 2030. So they want to achieve with nuclear power in 20 more years what renewables are supposed to be able to accomplish in only a few years. It's only 4 years to 2030, isn't it? So, and the other final points I want to make is that batteries are getting cheaper and better, so much so that in Texas in 2025, December, they had they drew 10,000 megawatts of electrical power from batteries. Now that's equal to the Wesleyville project that I was just showing you earlier. 10,000 megawatts. That's almost equal to all the nuclear plants installed in Ontario, which is about 12,000 megawatts. It's also close to twice the operating capacity of Texas 4 nuclear reactors. And of course, some people say, well, yeah, but if you get rid of nuclear, aren't you going to greenhouse gas problem? It's going to get bad. Well, here's Germany. They phased out all 17 of their nuclear reactors. They shut them all down. They've used a lot of wind and solar, and they have been reducing their greenhouse gas emissions steadily year by year ever since. Their total emissions have declined by 30%. In the energy sector, it's 50%. So without nuclear, they're doing better than other countries are with nuclear. And that's the end.